Thank you, Stan, for that introduction. So for the guys who are confused, what is the AI talk doing in an open source track? This is open source. AI can be open source as well. And for the guys who are, and the gals, who at 4:30 are wondering, hey, can you make it short and sweet? Yes. So let's get started with that. The topic for today is learning from names. This is a project that I've done with a longtime collaborator, Suryan Lau Prapanon. He lives in Thailand, I live in the US, and we have had a long collaboration. So let's get started. The first question you may have, right, when you get started with this is, hey, listen, why do you want to learn from names, right? And I have an odd answer to this, which I'll kind of give you greater clarity about as we go a little bit further. Well, because sometimes all you have are names. I think we should replace the R with a is. Media, most voter file lists, they just have names, right? So what do I mean by that? Let's just double click on the media portion. This is just something from earlier today from the New York Times, right? I don't know if you guys can see this, but there is William Barr, and then our man Bob Mueller, who is kind of making his presence felt, right? If you wanted additional data on who was covered, that's all you get, just names, right? It is your job to kind of impute other characteristics about who was covered, who was cited. And that's what I mean, that all you get sometimes is names. But let's kind of expand this a little bit further. So why do you want to learn from names? Because you want to highlight biases, fight biases, prevent biases. You know, in machine learning, you've all heard of the hidden bias that we get when we ingest a text corpus, which has some of the biases which have been built up around how people have traditionally kind of talked about women, people of different races, and then you uncover those associations. If you wanted to regress some of those things out, then how do you do that, right? Part of the thing that you get to press your hand on is if you had metadata on names. And then there is this odd thing about personalization. And I know that our mind wanders to sort of crazy theories about personalization, which are suboptimal personalizations. But I'll give you guys some concrete examples about some healthier examples of personalization. So if we are going to be concrete about this stuff, let me just give you examples, right? We have talked about the fact that if you wanted to study biases in media coverage, and then also who is cited as a source, right? Are African Americans cited as sources? Because you remember that the modal media trick today is, what is the man on the street's opinion about X, Y, or Z? So how often is it that the man or the woman on the street is an African American, is an Asian, is a Caucasian, belongs to a certain ethnic group, is a man or a woman? That's something that you could learn from names as well. If you wanted to study fairness in lending, and then all, you know, in interest of disclosure, Zillow reached out to me 6 months ago to study precisely that. You want to know, are African Americans being charged higher interest rates than Asians? Well, how are you going to study that? You can rely on self-reports, which are sometimes noisy, or you can try to impute other metadata about the names. And then there is another aspect around political accountability. If you wanted to study and highlight political accountability kinds of questions, you know, you could say, hey, listen, I'm going to send out an audit study or do an audit study, and I'm going to manipulate which name this email is going to be from, right? And I could kind of regress out and back out how responsive are politicians to emails with the same content, but with different people, right? And we could uncover these biases. And then when we talk about personalization, I wanted to highlight there is a study by Olson et al. In 2018, the economists, as far as I remember, And they find that African-American outcomes, health outcomes, tend to be a little better when they are being treated by African-American doctors. And some of it they think is because people feel implicitly that there is a more trusting relationship, communication relationship with them. So there are some healthier aspects of personalization when you're thinking about if we wanted to kind of use names to infer other things from names, right? So we have covered why learn from names, and there is an extra space between why and learn, and that is going to be filled by why not learn from names, right? Because we have covered why learn from names, and then you're saying, hey buddy, you just covered half of the ledger. I'm screaming to tell you why not learn from names. Not that it is in either of our control, right? There are people who are already doing it. Because you all fear, and I share that fear, that if we learn this metadata from names, people will actually use it as an instrument for discrimination. Not to prevent it, not to fight it, but to actually discriminate, and in negative ways. And I would say that it exists for each of the ML things that you learn about people, right? Whenever you learn something about people, it can be used suboptimally. For example, if you had credit risk scores that you could predict, you could actually use it to enable predatory lending. We could find out who are the people whose credit scores actually are really good, but we could hustle them to get a higher rate, right? But I admit that there is still a concern, and that is a concern we'll have to live with in the age of big data and ML. So let's now answer the question, if we wanted to learn from names, how would we kind of do that? So half of the auditorium may say, hey buddy, I got it. I got the answer. It is just estimate the conditional probability of ethnicity or race given a name, right? Just give me, I'm sure that there is a list of data which contains all the names and the ethnicity of each and every person. And what you just need to do is just estimate this conditional probability, right? And then what you do is classify to the majority class, or if you're smarter about this, what you can do is just estimate each of these proportions and say that those are actually the real proportions. And the virtue of, if you had all of this data, right, is that this is the Bayes optimal classifier. You cannot beat it. So what am I doing here? Why am I using machine learning? And the funny thing is, there is a census last name data set, which has counts for all the last names in the US for names which are shared by at least 100 people. Last names which are shared by at least 100 people. But the split by race is only available for the top 1,000 names, okay? And the data looks basically like this. You can kind of go on the website tomorrow, later today perhaps, if you wanted to skip the party, and which I'm told by Stan you shouldn't. It's apparently the saving grace of Anaconda Con. You could kind of download this data. But I wanted to focus your attention on this little thing, right? 1,000 most common last names. So guess how many last names are there in the US, for the entire population? I'll give you a hint. I'll actually, phrase it as opportunities, classify another 160K plus last names. So classification and supervision are canonically useful when we only have data on just part of the, so it seems that I have, the volume has gone up, perhaps by demand, but okay. That's why the hesitation. So how would you classify another 160K last names? And what I wanted to say is that machine learning is canonically useful when you don't actually have labels for all the data, right? That entire corpus. You have it only for a limited section of the corpus, and you want to extend it for the entire corpus. The opportunities where we can kind of do even better perhaps exist also when we have data on the first names of people. And there are a variety of scenarios where we'll have the first name, not just the last name of a person. And canonically, African Americans have somewhat more distinctive first names vis-a-vis the last names. If you're just looking to discriminate by race, and I'm not saying that, and I use the word discriminate in a semantic, that is, we wanted to just classify. African Americans versus, say, Caucasians, first names are a better guide than last names. And then machine learning can be helpful when people have multiple minor variations of the same last name, of the same basic last name. And then you can also kind of see that there are cases where you have geographic variation. Census is just giving you national data, and it may not be particularly useful in a variety of scenarios when we are looking at predicting the race or ethnicity or gender of a person who's sitting in, say, Austin. If you know a little more about the person, you can generally make better predictions. So then how do you capitalize on the opportunities? Well, the canonical go-to trick is find the patterns in the names, right? And here it comes down to capturing sounds or sequences of sounds. And of course, I'm not quite doing that in what I'll show you in a bit. But there is work underway which actually precisely does that. And there is an approximation to this that I'm currently doing. And I'll speak of that next. So if you were to talk to a modern NLP person today, phonemes used to be a thing, and then they were dead. Modern NLP kind of killed them and replaced it with bicards or bigrams or trigrams. Or sometimes just context. So does anyone recognize the sequence of bicards that I have here, and can you associate it with the name? Is there a Kim Kardashian in the house now? So this is a very canonically Armenian name that will have Ashian sort of in the end. Another canonical sequence of, if you wanted to think about names, Johansson, classic Swedish name, right? So that's when I talk about sequence of characters, that's the kind of sequence of sounds. Those are the kinds of things that I'm talking about. There are other people who have capitalized on other information. If you have information about who are you communicating with, and you have their names, then you can kind of, if you have labels on some of those things, then you can generalize and impute labels for people you talk to. Because people apparently talk more to co-ethnics or send emails more to co-ethnics than to, even in today's age, which is just bizarre and surprising and, but true. So Skiena, who is a professor at Stony Brook, I think, has done it with great success. And I think he's using it with Amazon. So here's the 101 on, we have done this portion, right? That is, this is the thing, this is the information we'll try to exploit, but how do you exploit it? So the 101 of machine learning, text classification is as follows. You get text, you create embeddings, you learn a classifier on top of those embeddings. That's it, 3 steps. And by embeddings, we mean that you are the company you keep, okay? You're kind of learning yourself in relationship to the other common bigrams or bicards that you see around you. Always use a large corpus for this and learn the context well. And then preserve tens or hundreds of vectors and then apply them, then pass them on to a model, classification model. It can be fully connected deep learning neural network with maybe 1 or 2 layers, works out beautifully most of the times. In our case, we are learning embeddings of common bicards, and we are applying LSTM on top. LSTM, for those who don't know, and this is not AI track, that's why I didn't quite go too far into this LSTM thing, is basically it is able to get long-term dependencies between sequences. Just to give you an example of that, but by that I mean the dependency between, say, an AS and an AN, if you will, in the first, in this one, right, AS and AN. And we can learn this in a sort of automated way. But okay, we'll know how to code, right? What information to exploit. Now the question is, what is the dependent variable, right? What do you mean by race and ethnicity? Let's start with how would I describe myself? I may describe myself as an Indian, but there is systematic variation across names, across linguistic groups in India, right? So you could kind of further subdivide and tell me this is a particular kind of Indian, if you will, right? The nuance of race and ethnicity is really in the eye of the beholder. And the closer you meet your people in the same ethnic group, they're like, no, you're still quite different. Because they're able to drill down and say, no, they're able to appreciate or able to segment themselves yet further, right, into yet further nuanced gradations of ethnicity. I like this one. Are you willing to fight for the group? Or maybe race and ethnicity are how people choose to describe themselves if they were given free text, right? And often enough, they're not, right? What we have generally is we're going to force fit you into admin categories that we have pre-hoc decided, which are somewhat important to the society. And these are things which continue to evolve, right? What gradations are important, how you grade people, how you kind of, those things continue to evolve, but that is sort of the broader ecosystem from which most of the data come from. So talking about where the data come from to the data itself. So I'm exploiting voting registration data in at least the open source portion of the project that I have released online, is voting registration data from Florida. So there are about 14 million people on which we have crudely coded race and ethnicity, for which we can actually exploit this to learn these associations. And you have it, technically you have it from multiple states. Not all states will give you the race and ethnicity of a person, but more than one do, okay? So another one is, I think, North Carolina. We have a few other states which will do that. And then the second data source that I exploit is one collected by Skian et al., which uses basically what I'll call the famous people data set. And they are scraping Wikipedia. And Wikipedia has these beautiful fine gradations about what ethnic group can claim a particular famous person, if you will. So since this is not the machine learning portion, I'm just going to kind of give you straight away move to what kind of success can we expect or do we see with a sort of a one-on-one plain vanilla model with this stuff, right? So this is just the F1 score, which is just basically we have precision and recall, right? This is a weighting of that, right? And what you can see is that for non-Hispanic whites, you can actually do very well. And the other thing that I have pointed out in red is the non-Hispanic blacks. If you just use their last names, you're just able to have an F1 score of just 0.32, which is pretty bad. With a full name, you're able to go as far as 0.5, which is still not great, but this is really plain vanilla 101 kind of a thing that you could do starting tomorrow with the data that is available. And then there is a simple application, and I want to lead you through just about how you could kind of use this data to kind of understand some of the things. So we're going to study donations to political campaigns in 2000 and 2010 by race and ethnicity. So the thing that I've highlighted in red is firstly, the Hispanic percentages are pretty low. This is the share of total donations which are coming from different ethnic groups, which are imputed. Caucasians or whites are, non-Hispanic whites are about 70% of the population in the US. They are vastly overrepresented. That's why I have this 86.5, right, in the political donations. And then Hispanics are vastly underrepresented. African Americans are about par, and Asians are somewhat underrepresented. And that may allow you to see, right, the representation patterns that you see sometimes, or it may allow you to connect these kinds of things, right? And the campaign finance data, for example, just has names. It doesn't quite have race or ethnicity. So we're using this package that I'll show you guys very quickly how to use it to kind of answer these kinds of questions. So this is the Python package. Let me just kind of do the 101 pandas thing for you guys. And it is, live code is not great, but you import your pandas as PD because it has been mandated somewhere. And then the package that I have, which you can download online today, is Ethnicolor. And we are exporting two functions, or importing two functions. One is called census ln, that is census last name. And the second one is called pred census ln. What census ln is just giving you is just the last name data that census has. And what the predicted census ln last name data function is giving you is an LSTM model at the back end. So what we're doing is, okay, just give me 1 second. And so we're just importing a small list of dictionaries, which we are going to now condense into a data frame. And then, you could get something like this, right? If you wanted to do pred, census ln, and do df, and then do name, it will take a little longer, but it should give you something. So you see something, if you're just using the census data, these numbers are going to look pretty similar to what you find here, right? And that's to be expected. But let me go back, and let's go to view full screen. Just give me a second. So I wanted to kind of close with, because this is an open source track, about what are the general principles of packaging ML. Tomorrow you guys will be writing software, and I just had, having exposed a couple of ML models through open source packages, I just wanted to lead you through what are the common principles. For me, clean API is pretty important, right? But what are the general principles underlying a clean API? So the question you may want to ask is, does the relationship between X and Y vary by time, vary by space? And then whatever variation is not captured in the X's in arguments, you need to capture it in the arguments to the API. So for example, I have the Florida voter registration data, right? So you could say that this model is generalizable just to Florida. So this is variation that I haven't captured in the X's, but I can pass it as an argument. That if you wanted a best guess of tomorrow a person about whom I have no information from Florida, that's my best guess. That's how you could pass this. Then the question is the model fixed? If the model is not fixed, then you may also want to do model versioning. But there's a nuance also to model versioning, because I think most model versioning is incomplete. So how I think about model versioning is the API call for the diffs in version should have three things. What is the different data? What is the different models? And what is the different errors? And the last bit is super important, but so are the first two bits. If you are able to, within companies, expose these kinds of things that allow for greater clarity about what is it about the model that has changed, and how has it changed the outputs. Generally, you wouldn't expose errors in a generic form. You will try to expose it through group bys around relevant things. And then, there should be an API call which kind of gives you model performance on some key benchmarks. And then I would also add a fail-safe on each of these predictions. If this data doesn't arrive, what is your fail-safe that you would predict? Is it a NA? Is it that you impute the data? Is it that you say, nobody, can't do? So that's it. I'm happy to kind of answer questions, things like that. I'm done.